This is geometry lesson 13.1. It's called the side splitting theorem. So the big idea says when two transversals intersect parallel lines, proportional lengths are created. So you have parallel lines, they get cut by two other lines that are not necessarily parallel. Those are your transversals, and we end up with lengths that are proportional. So we're going to look at this specifically in triangles. So the triangle side splitting theorem says if a line is parallel to a side of a triangle, so picture what that looks like. Here is a triangle. We have another line that's parallel to one of the sides. So DE is parallel to BC in this problem. So when that happens and it intersects the other two sides, so DE hits both other sides of the triangle, it's parallel to BC. It also hits AB and AE. It splits these sides into segments of proportional lengths. So it's going to cut these up proportionally, meaning the ratio of these two pieces are going to be in proportion to the ratio of these two pieces. So we can set them up using cross multiplication in a proportion and solve for our missing sides. So it's actually very simple here. So we're going to use the lengths as shown in the diagram at the right. DE is parallel to BC. We need that information to make this true. If DE was simply just a random line cutting through the sides of this triangle, it's not going to cut this up proportionally. But because it's parallel to BC, it will cut these up not necessarily into equal pieces, but proportional pieces. So 10 is going to compare to 15, the same way 8 is going to compare to whatever number this is. So first we're going to find AE. So I'm just going to call that X. Because these are proportional, according to this theorem, I can just go ahead and set up cross multiplying. So I'm just going to kind of set this up because I think it's easiest in the way that it sits in the picture. So I'm going to say 15 compares to 10 since that's the way they're stacked up there. The same way that X compares to 8. That's what this theorem is saying. That's true. If this is parallel to this, it's going to cut these up into proportional pieces. So I can set up a proportion. I'm going to cross multiply. 8 times 15 is 120. 10 times x is 10x. I'm going to divide by 10. And x equals 12. So that means AE out here equals 12. Okay, now find DE. So DE is right here. I'm going to call it y. And let's make sure we know this doesn't mean like times or something. X equals 12. All right, to find DE now, we don't have information from this theorem that says this is going to follow the same thing. So I can't do like 15 compares to 10, the same way this compares to 18. That's not the course of action I'm going to take here. What I'm going to look at is the fact that I should have similar triangles here. So just like these are in proportion to the whole thing, and I have these angles, this could be side angle side. But even simpler, I know these are similar. The small one, ADE, is similar to ABC by angle angle. So they both have A, right? The small triangle and the big triangle, they both use A. And if this is parallel to this, then these are corresponding. Okay, these are corresponding angles. So angle B is going to be equal to angle ADE in here, and same thing over here. So if I have matching angles, I know they're similar. So this just goes back to the last chapter now. I can go ahead and just look at the individual triangles and set them up in a proportion. So I do need to be careful here. When I compare, I'm not going to go 15 to 10 when I set this up. It's the side of the triangle to the side of the triangle. So 15 is the side of this triangle. The side of the big triangle is all of this, which is 15 and 10 together, which is 25. So when I go to set up this relationship, side of the triangle compared to side of the triangle, 15 compares to 25. The same way this side of the triangle, which we'll call y, compares to the same corresponding side in the other triangle, which is 18. So be careful. I can't just grab 15 and 10 and then say y over 18. Now I'm comparing sides of the triangle when I'm using this. So the side splitting theorem is just comparing the slices of the sides. You can set those up proportionally. And then if I'm going to actually use the line that's parallel in here, that's going to be a side of a similar triangle, and we set that up as such. So 15 times 18 comes out to 270, and 25 times y is 25y. If you need to draw the little circles to remind you what you've done, go ahead. We'll divide by 25, and 270 divided by 25 is 10.8. So DE equals 10.8. All right, so lots of setting up proportions here, cross multiplying. The math's not difficult. We just got to make sure we're grabbing the right things from the picture. So the converse of this is true. Remember, converse means you kind of switch the order that we're saying this. So here we said, if these are parallel, then these are proportional. And now we're going to say, hey, I have this line. I don't know if it's parallel to BC, but if I check and see if these sides are proportional to each other, and they are, I now know this is proportional. So it's the opposite. If they're parallel, then these are proportional. If they're proportional, then they're parallel. So we're just kind of working backwards here. So if a line intersects AB and AC in distinct points on the side of the triangle, and we find out that AD over DB is the same proportion as AE over EC over BC. AE over BC, that seems like a typo there. So this should be EC. It's a typo from the book there. All right. AD over BD is going to equal AE over EC. Typo there in the book. Then DE is parallel to BC. So same theorem as this, just working backwards. So here's a real life example where a contractor might actually use this theorem. And now they probably wouldn't say, I use the side splitting theorem to, no, they just know that this works. So when putting siding on a building, it's important that all of the pieces are parallel, right? If you go by a house and the siding is off a little bit and not all parallel to each other, that's going to look ridiculous. So suppose the siding installer has this triangular piece, this section of the wall, and he needs to make sure that the piece on the bottom of it runs parallel to the top, because it's easy to get off a little bit, and then by the time you get to the top, we're all over the place. So the installer has measured Z to P, so this piece is 8, P to Q, that this is 10, Z to R, that this is 6, and R to S, that this is 7.5. So up here in this triangular region, he's picked points across here, and he thinks the line he's drawn across here is parallel. And so he's measured these distances, and as long as these are proportional, if 8 compares to 10, the same way 6 compares to 7.5, he can guarantee that these pieces are actually parallel to each other. All right, so all we have to do here is check and make sure that this works. So 8 over 10 has to be the same as 6 over 7.5. Those have to compare the same way these do, and that guarantees that this is in fact parallel. So you could go ahead and reduce these fractions. We've talked about if you want to reduce this one, you're going to have to move those over a little bit. So this would become 60 over 75 if you want to reduce it as a fraction, and then 8 over 10 is also 4 over 5. So you could do it that way if you remember how to move the decimals to make that work, because if you just do 6 over 7.5, it's going to give you a decimal. But giving me the decimal in this case is not a bad thing. I could just divide. 8 divided by 10 is 0.8. 6 divided by 7.5 is 0.8. All right, so if I'm dividing these and I'm getting the same decimal, that's enough information to prove that these are equal to each other. So I could just say, hey, this is 0.8, and then this is 0.8. I don't need to leave this as a ratio. I just need to know that these ratios are equal. So the decimals say that they're equal. So because of that, I now know that piece F is parallel to piece A. And you could say PR, that line, is parallel to QS. But specific to the problem, it says, is piece F parallel to piece A? That's what we're trying to get at here. And that is true. Okay, flip to the back. One more problem like this. So in this example, we have a ramp. It's 15 meters long. And it's being built at the entrance of an office, blah, blah, blah. So they've put these supports here. They must be parallel to each other if they're going to support the ramp. If one of these was tilted the wrong way, this ramp is not going to be sturdy. So we need to make sure that these supports for the ramp are parallel to each other. If we have these measurements, where those supports are hitting the ground and then also up on the ramp, we can figure out if they're parallel without trying to use a protractor or something like that to see, is it 90 degrees? Because in real life, bigger version, you're not going to be able to pull out a protractor necessarily and measure that. Now, there's other tools, of course, that they have that could figure out if that's parallel, but this is a very easy way to do it. You just measure these lengths and you make sure that they are actually proportional to each other, and if they are, then I automatically know those two lines are parallel. So I'm going to set this up in a ratio. 9 compares to 6 the same way that 8.7 compares to 5.8. I don't know that for sure. I'm just trying it out here. So if I do 9 divided by 6, I get 1.5. 8.7 divided by 5.8, I also get 1.5. That checks out. So I have proven that BC is parallel to ED because these ratios are equal. Those pieces are proportional. If these did not come out equal, I can now say without a doubt these are not parallel to each other. There's an issue, and I would need to fix it. And again, if you wanted to compare them just as fractions, you would use your fraction function. 9 over 6 is the same as 3 over 2. And then what you would do with this one is slide those decimals over. 87 over 58 is also 3 over 2. So you could do it that way as well, but decimals is probably easier in this case. All right, and this is also true. It's true for any parallel lines that have these transversals going through it. And so two pairs of parallel sides, or one pair of parallel sides, I should say, two lines that are parallel, if they're connected, form a trapezoid. So I've got this big trapezoid right here. The trapezoid side splitting theorem says the same thing. If there's a line and it's parallel to the bases, remember in a trapezoid, the one pair of parallel sides are the bases. So this is base 1, this is base 2, or vice versa. Now I have another line that's parallel to both of them, and it hits both sides. Then the lengths of those segments created on the side are proportional. So let's go ahead and solve for the missing piece. A is 30, B is 24. D over here is 20, and we're missing C. So based on this theorem, these bases are parallel. I have another line going through, not diagonally or anything like that. It's parallel to the bases. It will cut these pieces up not equally, but proportionally. So I can say 24 will compare to 30 the same way. And then make sure you're consistent. I went from top to bottom. C compares to 20. I'm going to go ahead and cross multiply those. 24 times 20 is 480. 30 times C is 30C. Divide both sides by 30, and 480 divided by 30 is 16. So C must be 16. You could always go back and test this out and make sure you do get the same thing. So 24 over 30, what would that equal? I could divide. You see it's 0.8. Or I could have simplified and got 4/5. And if these are proportional, I should get the same exact thing with 16 over 20. So if I do 16 divided by 20, it's 0.8. And if I simplify 16 over 20, it's 4/5. So this was just a quick check. You don't have to go through that every time. But if you're telling me that that answer is 16, you can go back and check your ratios, make sure they're equal, and then you know you've got it all set.